Hello everybody and welcome to another video. Today I'm going to talk about a very low level implementation in C, which can also be applied to C++. And since C++ is essentially C, make no mistake about it, even there was once upon a time where one subset of a compiler was translating to first C code and we were getting C++ from C++ into C. But that's neither here nor there. That's just throwing it out there. What I will be trying to do in this series is re-implementing the struct and union keywords from scratch. In other words, I'm using struct and union without using those keywords. It's almost the same as that video implementing for, if, and while statements without using those statements, since we've broken down what they actually are behind the scenes. So in order for me to come up with this translation or approach or implementation, I had to look at what the assembly output is, and the assembly output of your respective struct and union is never a union or a struct in any sort of way. It's just memory offsets with moving certain things or certain data into registers, and that's how your struct and union works. It's not like a hash table in Python, though in Python we cannot define it as we can define it as a non-hash table object, but behind the scenes that what dynamic classes are in Python. But it's not even that. These are just points in memory, offsets in memory. Once we get to access them. So pretty much the structs and unions are a compiler's schema to represent your memory access and memory moves. So if I reveal the linked code behind moving my integer into supposed struct, I will see that I'm moving rbx minus 112 into this piece of memory, which is at that time EIX register. Now if I reveal the linked code for my const character pointer, I'll see that I'm moving that into rbx minus 24, but here I'm moving EAX into rbx minus 32, and that is because in order for us to get to a const character pointer, we'll have to do +8 since the size of const character pointer or any pointer in C, since there are all, and C++, they're all size t's essentially, it will be 8 bytes. So that's how it's done behind the scenes. This is not a struct, it's just a place in the memory and nothing other than that. So my motivation came from while I was using x64 debugger, there is a feature where you can turn your respective assembly output into, you can transpile it into C++. And the code looked nothing like my original C++ code. That is because the compiler uses all of the structs and all of the unions and even all of these high level types. This is all high level, and and compiles it into the assembly in such a manner that all of these things are not needed and are not they are just compiler types. So it's all and schemas in the case of struct and union. In other words, they're just optical illusion. And once you get that to the assembly, it all just becomes integer pointer u, size t, and nothing really is a high level type anymore. And I like to use the expression they are lost in translation. Even though that transpiled code C++ can work theoretically and effectively, um, it's not something a human would write for maintenance problems and other problems as well in your code. But still, it's a fully functional code, but it has nothing to do with the C language. And GCC, actually, it does have something to do with GCC, since it was GCC who compiled that code, but it has nothing to do with the original C language, or C++, depends what translation you're looking at. If a certain language outputs something onto the assembly, where the assembly is the target language, like we are breaking down now, it doesn't matter. All of this stuff gets lost in translation. And once we take that C++ disassembled code, it's not C++ anymore. So while there can be some indications that it might be, if there are some things in the text data segment that would reveal that. Anyway, this is all for learning purposes and learning purposes only. Never write this kind of code for many reasons. We're just writing it for us in order for us to understand and grasp what it all can be behind the scenes, but still at a high level here. So there are many videos where we are using unsigned character in C++ static storage implementation, C++ optimizing move, and destructor semantics. But however, this has nothing to do with C++. It's just a C type. So I decided to use that as our basis for an struct object here, since I'm able to apply type tuning here. And what type tuning essentially is, if you check it out on Wikipedia, it's just a way for us to cast from one type to another, from one offset to another, which would be impossible to achieve within the bounds of the formal language. So since we won't be using struct or union keywords, this is the way to go for us. And the first downside of this, as you might think, is we cannot return this object from if we write it in a function. So all of your functions would need to look like something like this. Make object, and then we take this as a pointer, an assigned object, and then mutate object here. So we cannot return, we can never possibly return this from a function, so we would need to write it at and refer to it at the main level always, and that is just nuts. As we can have nested functions and stuff like that, we're never really able to return this buffer because automatically um, any kind of memory on stack is deallocated. For lack of a better word, to be honest, in the assembly itself at the end of that code block. And it's not necessarily the allocate is just a sub operation in assembly, since I would use the allocate for something on heap. Anyway, how do we do this? We understand that the union takes the largest elements to hold one active element at a time. So I've taken the const character here and I applied size of. Now I can apply my type tuning where I'm getting the, and I don't need to do any kind of other uh, shifting or data offsets shifting of that pointer, since I'm only modifying one element at a time, so it's always going to be 0. So if I reveal this code, and by the way, this is the code for a typical struct where we have, if I reveal the code for a typical struct, you will see that we have moving stuff onto the RBX register, and essentially that's how we constitute the struct object. And if I reveal the linked code for this, it's a lot of code, and that is because this approach is just very verbose. So without any optimizations, it will look very chunky in a way. But if we apply just one optimizations, it does something very similar to what we are doing with the built-in struct. We take in, let me see the move. Okay, move, scroll to source. We are taking 132 and we're moving it onto RBX minus 64. So we are essentially, and there are a lot of checks in here where we have to ensure that we are not over the limit of the integer. So there is additional stuff since this. Now I don't know what all of this stuff does, but there's a lot of additional stuff when you're rolling with your own custom implementation of something. So we're doing pretty much the same moving for, and it's gonna be RBX minus 64 as well, for our const character pointer member. And now the active member is this one. And that is how exactly union behind the scenes works. That is why the union holds only one active member at a time, since it overwrites or overloads the previous one. I wonder how it's gonna be the code for, yeah, for O3 optimizations. And then we jump to assigning 132. So that is our implementation, and I made sure to add asserts in here and to make sure I can do something with those values. And also I did this because I don't want my code to get lost at O3 level, since unused code at sometimes at O1, O3 level is just cut out. Now if we look at the implementation of a struct, now that is a little bit different because in a struct you have a padding and you have to um, sum up all of the sizes of all the members and then have your object on stack. And never use this in any production level code. This is just purely and only for learning purposes. So what I'm doing here is that I'm adding manual padding since there is no way for me to write the front end of the compiler, and I only did this because I deduced that from size of struct object this is 16 with the padding. So this is 4 bytes and this is 8 bytes. But we should always, by the way, order our members from largest to smallest in order to give a compiler the best shot at optimizing and making our padding as small as possible and still have everything behave at the same level, at the same high quality level. So what I'm doing here is that I'm taking size of int, size of const character, and +4. So in order for me to assign the first, in order for me to do this, where I'm doing object.I equals to II, I will need to access the first, the 0 offset of that pointer because it's located for me in there, and that's where my int will live from now on. And in order for me to assign the string, which would be equal to, which would be equivalent to object.string AAB, I have to take the offset of my int in order to advance up to that point of memory and assign my const character. And that works like a charm. But it just works like a charm. It doesn't mean that you would use this kind of stuff in your own code base, since the padding is, as I've noted here, is implementation defined. This is the information I found online. You would never, there are compiler rules, there are alignment rules, there are all sorts of rules that proves this approach or just renders this approach as breakable, as ill-advised, as just bad in every conceivable way. But that's how I would implement struct and union in C without using those keywords. So what we learned from this video is that you can do this kind of stuff and you can sharpen your knowledge of C and C++ by doing this, but you would never do this in a code base. And this is a huge disclaimer and warning. So I myself sharpened up my understanding of a union. I was always wondering, how can I implement a union? Why does it? How does it mark its own active member? Well, it just overrides the previous one because there are no memory offsets other than the starting point of your memory address, and it basically overloads the previous one, and that's it. Or in this case, overrides the previous one. And let me just take another look at the generated assembly for this one. Now this is much cleaner, I would say, then the union, since we are only doing what we would do in a struct object, but our union implementation is clearly a lot of assembly code. We have Leah, move, shifting. I'm not sure why are we having what does this jump do? Yeah, we are never gonna get to that jump since we're assigning 132 there, and we're gonna get to L5, which we get to the assigning. I wonder what this is. Let me just Google for it. Is an internal goal used by sanitizer. Oh, we are using the sanitizer. Holy moly. Let me just have that code now. Cleaner. Yeah, I totally just overlooked the fact that we are using the sanitizer. But the problem with this is now our code gets way too optimized. And now we are definitely getting cleaner assembly and what we would get for a typical struct. If I reveal the linked code for typical struct, it's rbx minus 32 and then rbx minus 52 for our string holder. And we have rbx 32 moving it, and yeah, there it is. We're moving it, comparing it, and once we get to the string, we're doing pretty much the same thing. Let me just reveal the linked code. So minus 32 and that's how it's done. However, I'm a little bit concerned that the compiler is this smart nowadays. It just understands that these are not used at all, and it essentially just translates your code into something like this. And it just doesn't care that we're using a struct or not. So it's really nuts, really. So that's why I have to use O2 optimizations in this case. But yeah. Anyway, that will be all for this video, and I hope you enjoyed it, and let me know what you think in the comments below. Thank you for watching, and until next time, take care.